Hello Algebra 1 students. Now for this video you're going to need grid paper and you're going to need a TI Inspire. So make sure to get both of those out, and then you're going to be taking down the same exact notes that I'm going to be writing on this piece of paper on your own paper. So make sure to pause the video frequently in order to get caught up on taking notes. So this is how we're going to label our notes. Algebra 1. The topic of this video is going to be systems of equations, and in particular solving systems of equations by graphing. Now let's think about what we know in the topic. We know how to solve equations. We know how to graph equations, at least equations of lines. So we're going to think about the pieces that we already know how to do, and then we're going to bring those pieces into this new topic, solving systems of equations by graphing. So first of all, let's have a little thought bubble out here, a think back. Think back. If I asked you to solve the equation, I don't know, let's say 4x plus 5 equals 13. If I ask you to solve that equation, you know what that means. Okay? It means find a number that I can stick in for x that will make that equation true. In this case, the answer is x equals 2. 2 is a number that you can stick in for x to make that equation true. And we learned some techniques to find that answer. Okay? For example, we learned that we could subtract 5 from both sides. So 4x equals 13 minus 5 is 8. And then finally we could divide both sides by 4. So x equals 2. Okay? So this is something that you're already familiar with. You know how to solve an equation that has one unknown, one variable, x. You know how to solve that equation to find the number that you can stick in for x to make the equation true. Now, we have seen equations that look something like this. Let's say y equals x plus 2. Now, it doesn't make any sense to say solve the equation y equals x plus 2. It doesn't make any sense to say that. Although technically it is solved for y in the sense that y is isolated and the equation is written so that y equals something. But otherwise, it doesn't make the same sort of sense that solve the equation makes over here. Okay? But why? Why does it not make any sense to say solve the equation y equals x plus 2, like it did over here? Well, because we have two variables here. We have two unknowns. Over here, we just had one unknown. So we knew immediately what we were solving for. We were solving for x. But over here, there's two unknowns. Right now, the equation is currently solved for y, but this equation doesn't tell us what one value y could be, because y could be an infinite number of values. It just depends on what x is. So really what we have here, in the way that it's written, is a function. Y is a function of x. That means that the value of y depends on what value x has. So right now this doesn't make any sense, but we can make it make sense by changing it up a little bit. Instead of just one equation, what if I gave you two equations? Say my second equation is y equals 3x minus 2. Okay? So I'm just pulling that out of a hat. But now we have to change the directions of the problem a little bit. Now we have two equations, so solve the equations. But now I'm going to introduce this new word, solve the system of equations. Now this problem makes sense. And in fact, this is going to be the type of problem that we're going to be studying in this next unit. I'm going to ask you to solve a system of equations. And you're going to know what that means, and you're going to know how to do it in a variety of ways. Today, in this video, you're going to learn how to solve this system of equations by graphing. So let's do that. These two equations, you should recognize these as being equations of lines. Right now, they are written in slope-intercept form. Okay? They're written in the y equals mx plus b form. So let's graph these. So you are doing this with me. So go ahead and graph them on your grid paper. You don't have to wait for me to do that because you want to be a pro at doing this. Let's see, I'm going to graph the first one. I'm going to graph it in red. Graph the second one in blue. So right here, y equals x plus 2. The y-intercept is 2. The slope is this imaginary 1. So that means that I'm going to rise 1, run 1. Rise 1, run 1. Rise 1, run 1. And so on. Okay? So this is a graph of the first equation, y equals x plus 2. Now I'm going to graph the second equation. The y-intercept is negative 2. The slope is 3, which means rise 3, run 1. Rise 3, run 1. Rise 3, run 1. I'm going to go backwards as well. I'm going to connect these bad boys with a line. Ta-da! Y equals 3x minus 2. Okay. Now, we've put together the pieces that we know. We have a system of equations, which just means two equations that are kind of linked together. And I just graphed each equation individually. So I know how to do that. I know how to graph these equations, because that's what we did in the last unit. Now, let's think back again to what graphing really means. Think back. What does graphing really mean? What does graphing mean? Well, graphing an equation means that any ordered pair on this line is a solution to that equation. So for example, this point right here. The ordered pair corresponding to that point is negative 1 is the x, and positive 1 is the y. So this ordered pair, negative 1, comma 1, is on the red line. That means that if I put negative 1 in for x, and I put in positive 1 for y, this equation would be true. 1 equals negative 1 plus 2. Negative 1 plus 2 is positive 1, which is true. Okay? So a graph of an equation represents all of the possible values for x and y that if you plug them in at the same time into the equation, they make the equation true. So back when I said that there's an infinite number of y's, an infinite number of values that you can stick in for y here, it just depends on what value you stick in for x that you get to pick one value of y. Okay? Now, when I ask you to solve a system of equations, what I'm asking you to do is find the value of x and y that you can stick into the top equation to make it true, and you can stick the same value for x and the same value for y into the second equation to make it true as well. So solving a system of equations means find the x and the y that makes both equations true at the same time. Now, if all of the ordered pairs on the red line make y equals x plus 2 true, and all of the ordered pairs on the blue line make y equals 3x minus 2 true, what ordered pair makes both equations true at the same time? Well, right there, the intersection of the two lines. The intersection point of the two lines represents the solution to the system. Now we can read off what the ordered pair of that point is. Over to the right 2, and then up 4. So 2, comma 4 is the solution to this system of equations. Now let's just double check that. Y equals x plus 2 was our first equation. If I stick in 2 for x and 4 for y, is it true that 4 equals 2 plus 2? Well, yeah, that's true. Now let's do the same exact thing with the second equation, y equals 3x minus 2. If I stick in 2 for x, and I stick in 4 for y, is this equation true? Well, let's see, 3 times 2 is 6, minus 2, yeah, 6 minus 2 is 4. So this is also true. Okay? So the big idea here is that you can find the solution to a system of equations by graphing the two equations. And the intersection of the two graphs, the ordered pair of that intersection point, represents the solution to the system. Alright, now get out your TI Inspire and let's do this exact same problem here, except using the calculator. Let's see how we would do that. So turn the calculator on, new document, so enter, and then we're going to go to add graphs. There we go. So we have a blank graph screen here. Now down here it says f1 x in parentheses equals. Remember, that whole thing just is the exact same thing as y equals. Now let's type in the first equation, y equals x plus 2. Enter. There we go. And it's unfortunate that is in blue, but that is the same exact equation that we graphed over here. Now let's graph the second one. Now in order to graph a new function, I'm going to press the tab button. So tab. Now f2x, so y equals 3x minus 2. Enter. And unfortunately it is in red, the exact opposite of what I have over here, but you get the idea. The graphs look the same. Now, I want to use the calculator to find out where those two graphs intersect. So watch what I'm going to do. I'm going to go to Menu, Analyze Graph, and then Intersection. Now right here, if these graphs were more complicated and maybe they intersected at multiple points, and we'll be studying that later on this year, then I could specify which intersection point I wanted by kind of sandwiching it between the lower bound and then soon the upper bound. So it actually doesn't really matter where I put this as long as it's to the left of my intersection point. So the lower bound needs to be somewhere over here to the left of my intersection point. Then press this button. Now it asks me for the upper bound. So I'm going to move over here and notice that this blue area tells me what is the domain that I'm interested in? What set of x values am I interested in looking at? So this is just an extra thing that you have to deal with in the calculator. We obviously didn't have to deal with it over here. I can press enter again, and then ta-da! Look at that. Kind of hidden in here, I'm going to take my red text, I'm going to click, wiggle my finger, notice how the hand clasps, and I'm going to bring this down here, and look at that. The intersection point is labeled 2, 4. And that is exactly what we found over here. So this is the way that you can use the graphing calculator to solve a system of equations by graphing. Alright, now I forgot about something. I want you to label this as example number 1. So go back, label this example number 1. And then now we're going to be looking at a second example. Example number 2. And there's some sort of fur on my pen. That is annoying. I think it's gone now. Example number 2. Okay, so let me give you another system of equations. So the directions are going to be solve the system of equations. And yes, I do want you to write down the directions in your notes as well. Solve the system of equations. And this is going to be the system. Y equals negative x minus 4. And then 4x minus y equals negative 1. Okay? So this is the new system of equations that I want to solve. Now, we are still in the the section on solving systems of equations by graphing. But when you look at this problem, you may notice a problem. The top equation is in slope-intercept form, and that's easy enough to graph. In fact, let's do it. So let's see here. Y-intercept is negative 4. The slope is negative 1. So slope, I'm just going to write this out here so it's a bit clearer. Slope is negative 1, which means you could say the rise is negative 1, the run is positive 1, so go down 1 over 1, etc. Or you could also say rise positive 1, run negative 1. They're both the same, so that means rise up, then left, up, left, up, left. Okay? So that is a line with a y-intercept of negative 4 and a slope of negative 1. Notice, of course, that we can double check ourselves. This has a negative slope, which means it's tilted downward from left to right. But, like I said, we're going to encounter a problem with this second equation. It is not written in slope-intercept form. So I can't see what the intercept is, the y-intercept, and I can't immediately see what the slope is. So I can't graph it. Not only that, but if I wanted to try to bypass this whole system, I can't even plug it into my calculator because it's not written in the form of y equals. So how in the world do I fix that? Well, we learned another skill. We can solve this equation for y. We can solve this equation for y. And this is kind of a different but related meaning of the word solve. This just means isolate y. Just like up here, y is isolated, which means it's written in slope-intercept form, so I can graph it. So I want you to solve this equation for y now, so that we can graph it. Now when I ask you to solve that equation for y, you're going to be using the same exact steps, the same exact procedure that you learned how to solve any equation for anything. Okay? It just means progressively move everything to the other side of the equation. In this case, we have to start with the 4x. So I'm going to subtract 4x from both sides first of all, because 4x minus 4x is 0. that goes away. I'm left with a negative y, and then I'm going to put the negative 4x in front, and then the negative 1 behind, because I can flip those around. That's alright. So negative y equals negative 4x minus 1. This still isn't completely solved for y yet. I need to get rid of that negative sign. Now technically the way I do it is by, you can divide by negative 1, divide everything by negative 1. Negative y divided by negative 1 is now positive y. Negative 4x divided by negative 1 is now positive 4x. And the negative 1 divided by negative 1 is a positive 1. So all the negatives cancel out nicely. So now our second equation is written in slope-intercept form. I can clearly see that the y-intercept is positive 1. So I'm going to graph that. Positive 1. And then the slope is 4. Which means rise 4, run 1. So rise 4, run 1. And then I can do the same thing except go backwards. Rise negative 4, run negative 1. There we go. And then I'm going to graph this. And again, just like with example number 1, the intersection of the two graphs is the solution. So in this case, we're going to go left negative 1 and then down negative 3. So the x coordinate of that point is negative 1. The y coordinate is negative 3. So that is the solution. And I didn't do this with example number 1, but this is what you should write out completely. Solution is negative 1, negative 3, or we can write it out like this. X equals negative 1, y equals negative 3. Now in this case, there was just one solution to the system of equations. That means that there's only one ordered pair, negative 1 comma negative 3, that will make both of these equations true at the same time. And that means graphically there's only one intersection point. But there's going to be a couple other cases that you might run into. So let's look at a new example. Example number 3. Let's say I wanted you to solve this new system of equations. Solve the system. Let's say y equals 2x plus 3 and y equals 2x minus 1. Okay? So let's approach this problem the same exact way that we did example 1 and number 2. Example number 1 and example number 2. We're going to solve the system by graphing. Alright, so I'm going to make this into I'm going to make the second one red this time. So let's graph the second one. 2x minus 1. Y-intercept is negative 1. Slope is positive 2, which means rise 2, run 1. So rise 2, run 1, rise 2, run 1, so on. And here I have a line. And then we graph the first one in blue. After learning my lesson with the graphing calculator, y-intercept is positive 3. And then the slope is, again, rise 2, run 1. Slope is 2. And then voila, I have a graph of my second line. First line, whatever. So this is y equals 2x plus 3. Now, you might notice something. these two lines are parallel. We can see that graphically, that they run alongside each other. We could also have seen this from the equations themselves. You may recall that if two lines have the same slope, like in this case, same slope means that the lines are parallel. And I'm actually going to put a little star next to this, because, not necessarily because it's important, although it is important. I'm going to put a star there because we're going to see a situation where two equations have the same slope, but you wouldn't quite call them parallel. Okay, so we're going to see that in the next example. But in this case, the slopes are the same, and the y-intercepts are different. That means that the lines are parallel. Now, because the lines are parallel, you know from middle school geometry that this means that the lines never intersect. But if the lines never intersect, and the whole point of solving a system of equations by graphing is to find the intersection point, what does it mean if the two lines never intersect? Well, it means that we can never find a solution. So there is no solution to this system of equations because there's no intersection point of these two graphs. The lines are parallel. They never intersect. So there's no value of x and y that will make both of these equations true at the same time. Now let's look at a third example. Remember my little star up here? Example number 4. What happens if I give you this equation? Y equals 1/3 times x plus 2. And my second equation is y equals, let's say 1/3 x plus 2. No, that was not a mistake. I did, in fact, write the same equation twice. If I ask you to solve this system of equations, I graph the first equation, the graph of the second equation is going to look identical. And in fact, let's go ahead and just graph them. Why not? Doesn't hurt to get a little extra practice graphing. So let's see here. The y-intercept is 2, and then the slope is 1/3, so rise 1, run 3, rise 1, run 3, and I'm going to go backwards a little bit. So here is the graph of the first equation, and of course it is identical to the graph of the second equation. And in some problems you might see this as a purple line, because red plus blue equals purple. So whenever you see a purple line in any problems, that just means that the two graphs are on top of each other. They are the same graph. Now what does this mean in terms of this problem? Solve the system of equations? Well, graphically that means find the intersection point, but there isn't just one intersection point, like there was up here. But neither can we really say that there's no intersection points, like in this case. Over here, the two graphs are the same, so that means that they intersect each other everywhere. They intersect everywhere along the graph. And in terms of the problem that we pose, solve the system of equations, that means that there are infinitely many solutions. There's an infinite number of solutions to that system of equations. That means that you can find an infinite number of ordered pairs, x and y, that make both equations true. Now this problem was pretty straightforward because the equations already look identical, but you're going to be encountering problems in which one equation might already be written in slope-intercept form, but the other equation will not be written in slope-intercept form. And so you won't be able to see immediately, like, oh yeah, duh, the two equations are identical, so the two graphs are identical, so infinitely many solutions to that system of equations. It's not always going to be that easy, but I did want to show you all three of these possibilities. In this case, there is one solution. In this case, there's no solution. And in this case, there's an infinite number of solutions.